And thanks much also to Fik and the organizer for letting me speak here. So this is joint work with Gabor Hetchy and Margaret Reddy. And here thanks to all the organizations supplying money for this. So here is a definition of the toric G polynomial of an Eulerian Poe set. And this probably is the worst slide I have here in my talk. But the thing you want to note is that if I have an n-dimensional polytope, its face lattice is an Eulerian Poe set, then the toric G polynomial goes from up to half dimension n. So these are the entries in the toric G vector. So why should one be interested in toric G vector? Well, Stanley proved that if you have a rational polytope, then the toric G vector or toric G polynomial is non-negative. But Calle Carew came in recently and he was able to remove the condition the polytope being rational. So can we compute any examples here? So here's the Combinatorics, for instance. So this is the n-dimensional polytope where you take all the permutation on n+1 elements, you put them in space, and you take the convex hull. So in 2 dimensions, you have hexagon. In 3 dimensions, you have the truncated octahedron. And back in Stanley's paper, back in 1987, he started computing these for the Combinatorics, and he got up to 5 dimensions. And then he stopped and said, what happens? So this is the question that motivated us to study the toric G polynomial here. So now we have to be a little bit technical. We can do this for simple polytopes. There's a polytope whose dual simplicial. We had the F vector, we're counting faces of each dimension. Then we can define the H polynomial or H vector by junction basis. Notice that this is different from the toric H vector on my first slide. And here we have the dense summing relation saying that the H polynomial are palindromic. When you reverse it, you get the same thing. So here I computed it for the 3-dimensional Combinatorics, and we get the H vector to be 1, 11, 11, 1. Well, there's another basis you can look at. It's called the gamma vector, that you subtract off rows of Pascal's triangle from the H vector. So in our example here, 1, 11, 11, 1, you subtract the third row in Pascal's triangle, 1, 3, 3, 1. But then you get 8, 8 left, and that's 8 times the first row in Pascal's triangle. So there's the gamma vector. What did I do? Yeah. So we have these polynomials we define, the toric G contribution polynomials. And you want to observe that in these polynomials, there's a negative sign involved here in x minus 1 appearing. But if I set j equal to 0, then I actually have the toric G polynomial of the n-dimensional cube. So they're actually extending the cube in a certain sense. Here are the polynomials, and you look at them and you realize all the coefficients are non-negative. And yes, they are. We have the following combinatorial interpretation of the polynomials. So recall that the sparse subset is a subset where you do not have for any element integer I and I+1 in it. And then we can now actually give an interpretation by counting permutations what these coefficients are. In terms of 1 to 3 avoiding permutations, there are sense set and counting a sense in them. So we know we have something nice. And the reason we're interested in these polynomials is that if you have the gamma vector of a polytope, of a simple polytope, then this allows you to compute the toric G vector of the polynomial, or of the polytope. So nice and consistent here. I'm going to need the following three notions of functions. So I'm taking a function f from the set 1 for n to itself. Then I have the classical notion of parking function. That has to do with parking cars. That's the definition. I also have the notion of a function being 1, 2, 3 avoiding. And this definition is basically the same variations, which is subclass of these functions. And then I also have this notion of an ascent, which is also stolen from permutation language. And now we can look at the first polytope I'm interested in, the ICECA2026. Okay, I haven't defined the ICECA2026 yet, and I'm going to give you a definition later on. But it was studied by Stashev back in the 60s, but even before that by Tamari. And the result is the following, that the Kf toric G vector entry in the n-dimensional ICECA2026 is a number of 1, 2, 3 avoiding parking functions having exactly k ascents. So we actually have a nice description here, combinatorial description of the toric G vector entries for the ICECA2026. And the proof we have has three important parts. The first part is due to Postnikov, Reiner, and Williams. That is that the gamma vector is given by the Catalan number times the binomial coefficient. And then the proof consists of using two bijections relating Dyck paths and permutations. And this bijection to Garcia and Heyman and Krattenthaler. The other class of polytopes interesting is the cyclohedron. And in the work of Rodriguez-Simeon, one should really think about the cyclohedron as a type B analog of the ICECA2026. And here I have fused word values of the toric G vector of it. And our result for the toric G vector here is basically the same result as before, except we drop the notion of parking functions. So now we're looking at all functions from on the set n to itself that we want to be avoiding and having k exactly ascents. It's a nice analog to the result. And strange enough, the proof is almost the same. Postnikov, Reiner, and Williams steps in, and the result for the gamma vector is that you replace the Catalan number with the central binomial coefficient. And the Garcia-Heyman bijection, well, is for functions and not parking functions. But when you replace it with functions, then it's for lattice path and not Dyck paths. So the whole thing works through very nicely again. But let's head down to the permutohedra. So I'm going to have the notion of parking tree. So it's going to be a rooted plane tree on n plus 1 vertices. And I'm going to label the vertices, I'm going to label the edges. And here are my two conditions. When I label the vertices with 1 for n plus 1, the label of a parent should always be bigger. Oh, I said the wrong thing. The label of a parent should be smaller than the label of the children. Okay, so that is that the labeling is increasing. And then we have to label the edges with 1 for n. And the only condition is that when you look at the edge labels associated with a parent, they had to also be increasing left to right. So why is this called parking trees? Well, when you take an edge label and you look what is the parent node of that one, and you write down the label of the parent node, this gives us a parking function. It's rather easy to observe this fact, so that's why the notion we call this parking trees. And then we studied all through the literature before. So now we can actually describe the toric G vector of the Combinatorics, completing Stanley's question here. Namely, the kth entry in the toric G vector of the n-dimensional Combinatorics is that we're looking at parking trees on n+1 nodes. They encode a 1 to 3 avoiding parking function having exactly k ascents. So the result is very much in the spirit what we had for the icosaedra and the cyclohedron before. Okay, now I had to admit I didn't define the icosaedra and the cyclohedra for you, and I'm going to do that in terms of the bigger class of nestohedra. So a building set is going to be set on a finite subset S satisfying these two conditions. And then for each subset in my building set, I can take the convex hull of the corresponding basis vector in space. And then when I take the Minkowski sum of all the sets in the building set, I get the nestohedra. This is a lot to take in one moment here. But let's look at 3 examples. If I take all the intervals of the set 1 for n+1, then the associated nestohedra is the icosaedra. If I instead change it to cyclic intervals, so I'm doing this on the cycle, then the corresponding polytope is the cyclohedron. And finally, if I take all the non-empty subsets of an n+1 set, then I actually have the Combinatorics. So they're all my 3 main examples here nicely fix in as this notion of nestohedra. Here's 2 technical conditions I'm going to need in building sets. It's connected if the big set is inside the building set. And it's going to be chordal if I take any subset in the building set and I can eat it up from below. I can throw out the smallest element and then it's still going to be in the building set. So I wanted to observe here that the cyclohedron is building set with the cyclic intervals. That's not chordal. So the cyclohedron is not going to fit in what it comes in like talking about now. I'm also going to need the notion of a Fuata-Striel tree. So you start with permutation. You locate the smallest element in it, which is 1. And everything that's to the before the 1, you send down left. And everything that after the 1, you send down right. So that's how the tree is going to look like. And then you repeat recursively. You look for the smallest element. You keep that in the node and send everything down again. And again. So there is the Fuata-Striel tree. A Fuata-Striel is also right adjusted if every node that has exactly 1 child has a right child. And we need one more definition from a person called Reiner and Williams. A permutation is B permutation if it contains the following, satisfy the following condition, which is very hard to first understand. You have to work with examples to truly understand this thing. But now we have the end result. We can actually give you the toric G vector for a nestohedra, corresponding to a building set with connected and chordal. Namely, it's going to count the number of parking trees, includes a 1 to 3 avoiding parking function having k ascents. And if I remove the labels on the edges, I'm going to get the right adjusted Fuata-Striel tree of a B permutation. which has no double descents and no final descents. So we can actually obtain the toric G vector for some of these things. So let me just end with an open question here. We were able to compute the toric G vector for these polytopes. Can you find other classes of polytopes we can compute the toric G vector? It's completely open. So thank you very much. And thanks so much for a nice first day of this conference.